Okay, thanks Manoj. So this discussion is about use cases, and when I looked at this topic, and many of us in the audience, right, we're all engineers, and we want to either build some kind of silicon or update software, or we may be the users of these, right? So looking at this use case discussion, and we really want to discuss something new because there is a lot of discussion around CXL, and we don't want to touch that over here. And maybe double click, a little bit onto these topics, and really give a message in the industry what really needs to happen. And after this use case discussion, there is a discussion on ecosystem readiness. So kind of builds a nice story around that. So with that, right, with the use case, we know that this is a new technology, CXL, and are there any real problems that we are solving here, right? Because sometimes we come up with certain use cases, but these may be the cooked use cases, may not be real problems. But we think that there are these real problems, right? One is there are a lot of these new use cases we all have seen, AI/ML, SQL, they need more memory, right? And how do we address that challenge? And there is a path now through this new technology, right? The second one is about reducing infrastructure cost. So we have heard many times that memory plays a dominant role in the server cost, and how do we reduce that? And the third point is kind of, the CPU guys are interested in putting more and more cores, and many of us who have done SoC designs, we know that DDR being a parallel interface, there is a limit to how many DDR channels you can put. That means your CPU to bandwidth or CPU to capacity, that is facing some challenges. So how do we add this additional memory? The fourth problem is sometimes the memory vendors, they have these new memory technologies, and if you cannot get on the CPU roadmap, then how do you enable that? So CXL kind of provides that path. And the fifth one, I think yesterday we all heard in the sustainability talk, is about how do we, if you look at the server, memory components have much more shelf life than the other components. So can we use some of these DIMMs? And again, this new technology, CXL, provides that path. So essentially, all these use cases are trying to solve one of these 5 problems, right? So to have some right context for this discussion about use cases, we really want to give 3 messages here. One is, what does this really mean for hardware? Hardware meaning the server design, right? What does this mean for software and firmware community? Because we are all product builders here, right? And we are all looking for some kind of a guidance here. And the third thing is, what does it mean for silicon? Because there are a lot of vendors who are trying to build CXL controllers, so what they should look at. So all these points are leading into that discussion. So looking at hardware, right? So one of the main points that we're trying to make here is, this is a new thing. Everybody will have different requirements. Servers will be 1 socket, 2 socket. Now memory is coming out of the server, additional security. If you have memory pool, how do we have the VM to VM isolation? Memories are going to have different form factors. E1, E3, we all know PCIe, right? And there will be different cabling solutions. How do we service this? If there is a DIMM failure, how do you address it without taking a VM down? So, and again, of course, the CXL memory controller have requirements. So all of this means that there is a need for a common memory trace specification, and maybe OCP is the right platform to address this common memory trace specification. So the next point is about software and firmware. Again, the applications will be operated in 2 modes, transparent mode or opaque mode. And for opaque, which is primarily hypervisor managed, there will be a page mover, hotness tracker. And firmware, if you are looking at pooling, there will be a fabric manager. So who is going to build that, and what are those requirements? How do you update this firmware? Now there is a firmware, and this is a new thing, so there will be firmware updates. how do you handle it securely, and again, how this memory is recognized in the Windows and Linux. So that's the additional work here, right? So with that, let me move to Microsoft's use case, which is a public cloud, and I'm representing few of my team members who could not be here. So let's talk about the Microsoft use case. So what is the Microsoft public cloud use case is essentially we have a lot of mixed workloads, and these are all virtualized. And we do not know how these, we cannot look at these applications, right? We cannot look at that code. So this is all opaque to us. Now, why memory is important is because there are two things we're addressing here. One is we're looking at the cost. So we say that memory is the dominant factor, right? But at the same time, memory plays a very important role on performance, right? So the challenge here is how do you address it through some kind of a memory pooling, and that's the challenge here. And another thing that we find here is there is a lot of this memory which is stranded, because many times what happens is when these vCPU and the memory is sold to our customers, there is some memory still behind the socket which cannot be sold. So we call it as a stranded memory. And to solve this problem, I think with CXL, now memory pooling is a very interesting alternative. And that's what we are looking at it from the public cloud point of view. So what are the challenges, right? So what's the gold standard here? One, for the memory, the gold standard is local NUMA memory, right? And we all know that with CXL, with all these additional cables, everything is going to be a little bit far than the local memory. And how do you really address all the performance of these VMs, right? And this is where this prediction-based VM management, and Microsoft has published a paper around that, and that talks about how we can allocate certain VMs in a different ratios, whether to a local memory or to a pool of memory. So really the challenge, because this is a mixed workload environment, the challenge is looking at those VMs and moving them according to their performance requirements, right? That's the challenge here. Now coming back to the three main points we addressed here, what is really needed on the system design front, right? We all know CXL is a standard, but sometimes what we hear in the ecosystem is there is a CPU vendors are there, CXL controller vendors are there, and memory vendors are there. But they all need to be aligned. They all need to work with each other. So interop is very important. And I already talked about memory tray designs. But what we really want is, even though we call it as a standard, make sure that all of these components interoperate with each other. That's really very, very important. So going to the silicon side, right? What is really needed on the silicon side? I think my font is too small here. Yeah. So if you look at the memory controllers, right? First time controller is coming out of the CPU socket. So the reliability is extremely important. Reliability, data integrity, and making sure that you hit the best latency is also very important. And of course, security is getting a lot of attention these days, and that's also important. And having support for multiple generations of the memories, so having that flexibility, whether you go with DDR5 or emerging memory or DDR4, that's also a very important thing. But third, and the most important point I would like to make here is, after a lot of time, there is something new in this industry, right, after PCIe, and we are all excited about CXL. But at the same time, we have to make sure that we build products which are achievable in the time frame that we're looking at. So keeping it simple, focusing it really as a memory, and maybe over the years, we can build more complex product. But initially, keeping it simple, because as you can see, this is a very complex orchestration. We are touching a lot of layers in the infrastructure, and there are different trains. There is server design train, there is a controller train, CPU trains, and aligning all these things properly is very important. So You don't want to get into situations where we are continuously spinning on the silicon side or the software side, then nothing is going to be accomplished. So having simplicity in your design is very important. The next thing on the software, I think this is where this memory, and there was a term, ZNUMA, zero core memory, and that work needs to happen. And the second thing is about, for Microsoft use case, again, this is all internal, but the prediction-based VM management. Fabric management is another thing, where we are talking about memory pool here. So how do we assign and deassign these memories to multiple VMs? How do we migrate VMs? How do we do some kind of QoS monitoring? Those things are very important from the fabric management. And as this firmware gets downloaded, because this is a new technology, of course there will be updates, right? How do we update it without impacting the performance? That's very important. The third one I would say, right, as we are developers, we really need to co-design this, right? This is something which needs continuous interaction between software, firmware, and silicon, and we should not be working in silos here. Otherwise, we will have multiple iteration of products, and that will be very complex to realize, right? So again, silicon, I know because I'm previously from silicon design, so having a very nimble approach towards your silicon is extremely important. We may find certain cases that we cannot think right now, but having that approach is very important. But finally, the message that I would like to say is pooling is very good. That can give us a lot of TCO savings, but at the same time, we have to always make sure that it's a memory, and having this focus on latency management at a cloud scale is very, very important to deploy it at a cloud scale. Thank you. So with this, I will invite Vikrant.
Thank you, Samir. Oh, Samir, were you supposed to talk on this one? All right. Okay, hello everyone, I'm Vikrant. I'm a hardware engineer at Uber, and I'll be talking about a use case that might resonate with folks who deploy microservices within containers. So it's slightly different from the public cloud use case, but I thought it's very relevant and very interesting in the context of the work that is being done in this project. So every time you open your Uber apps to order food or order your ride, and more recently I heard you can also order cannabis. It's only in Toronto, so don't open your phones yet. It triggers a sequence of events that is processed by a network of highly interdependent microservices. And as I'm showing here in the graph, it's pretty complex, and the dependencies grow over time as we introduce new features, launch new cities, etc. So each of these services have different amount of business logic and code complexity, depending on what part of the fulfillment process they are called in. And as a result, each of these services need different amount of compute resources. And when our capacity planning teams work with these service owners, they allocate capacity in terms of cores in order to ensure that they have enough resources per instance, but also the total number of instances needed to account for failover or bursty traffic situations. So then why focus on memory? What happens in this allocation process is memory is treated like an inelastic resource and gets tagged along in fixed ratios relative to the number of cores that are requested by the service teams. And because the billing is done in terms of dollar per core, memory is almost like is not attributed properly and is a hidden cost for most of the service owners. So there's very little chance for us to create any sort of governance or any sort of accountability to make sure memory is used efficiently from the beginning. And not surprisingly, what we find in our fleet is memory is a highly overallocated and underutilized resource. So pooling is a really elegant solution in my mind for us to amortize some of this headroom or the slack that is created by the underutilized memory and share it between X number of hosts, and then reduce the effective memory footprint of a fleet and thus the cost of capacity. So how do we make this happen? On our side, I think Samir covered most of the hardware aspects, so I'll just speak on a few things that we will require in our data centers. Definitely, we require support for multiple DDR technologies, like we have DDR4 and DDR5 is pretty pricey when it's launching. So there is a plan for us to reclaim our DDR. So definitely, we need memory vendors or vendors to come up with pooled memory appliances that can support multiple DDR generations. They should also be able to fit within standard form factor chassis and 19-inch racks, etc. In addition, we also need support for automation, for provisioning, configuration, and deployment of these appliances. Second, security is also an important aspect, especially as it comes to personal data sitting on an appliance that is external to the host. On the software side, we run Kubernetes for our container orchestration platform. And from what I know, we don't have enough support for Kubernetes to be able to provision or deploy the memory that is sitting in a pooled appliance. So that definitely needs to happen. And I'm showing a pool manager in a dotted box. I don't know if that's the right way to do it, but I'll let the experts figure it out. In addition, we also need the capability of doing predictive or pre-configured allocation of jobs relative to the affinities that they might have to the type of memory that they want to use. In this particular scenario where I was working with one of my peers on the Kubernetes team, we have two types of jobs. One of them is latency sensitive and very mission critical. Those could be affinitized to using local memory on a host. On the other hand, if you have a job that is latency insensitive, those could be using pooled memory that is sitting on the host or connected to the host. So those are some of the things that need to happen in the Kubernetes ecosystem. Unlike Microsoft, which is doing their own hypervisor and they have all this machine learning model that was built out on the slide that I skipped, we don't have that. We are going to lean on Kubernetes ecosystem to come up with these features. So I just want to summarize saying that I'm really looking forward to working with this group and peers in this room to implement this solution and really reduce or bend the cost curve for us. Thank you.
I think we'll be taking questions at the end of the track if there were. I know many people have, so please do hold on to your questions and let us know as we go through. I'll try to cover my material quickly because you may have seen some of it. Let me just talk quickly about two use cases that, as an example for, in general, memory expansion. One of them, it seems to is really driven by the growing AI/ML growth. One example that I'm taking here is especially in the search area of the recommendation models. Meta has deep learning recommendation models which are scaling significantly high from the size as well as the performance requirement. So the amount of memory that you need in a system really is driven by multiplication of those two things. How many features you are using, how many parameters you are using, and how many petaflops you are trying to drive in that platform. So as you talk about putting more accelerators in a system, it requires more memory, and at some point of time, you start really running on the system constraints of how much memory you can really accommodate. And this is where CXL can play a significant role for us as we try to expand the memory in those platforms as we are maxed out on the local connectivity. Second use case is actually the example of the use case is the caching and databases. This is different in the sense you still have capacity in the system that you can land. However, from TCO optimization perspective, you want optionality. You want to make sure that there are applications which are ready to do a trade-off of capacity to performance. At that, for example, caching requires more memory because they want to make sure that you can maintain the data for longer retention time in the system so that when you get a caching request, you can get a higher hit rate. And that is important for achieving the kind of QPS that you can have. So if you have a smaller amount of memory, you don't get a hit rate, that means your overall QPS is going to be effectively less because you want to make sure that you get to a higher hit rate. Databases, on the other hand, they are optimized for amount of storage you have on those systems, $ per terabyte. But to make sure that you can effectively use that storage, you need enough memory because then you can do the database queries at a high enough rate. So both of them are really optimized for a different reason. You want to make sure that they get effectively limited by, for example, for caching, you want to get limited on CPU, how much QPS you can drive. For database, you want to get limited by how much storage I can land. But to enable that, you need memory, and you need to make sure that that is very TCO efficient. So that's another use case that CXL can give you a very interesting opportunity when you have the system designed properly to make sure that you can use that expansion effectively through hardware-software co-design. In the interest of time, I'm not going to go through a lot of these details, but these are the major AI services we have, which are ranking and recommendations, computer vision, and languages. The reason we look at them three independently because their requirements are different, and that means the hardware that you design for that can be having a different optimization point. So we're looking at that and actually understanding that what are the memory requirements for them, what are the other hardware requirements for them is an important aspect for us. We focused, previous discussion was on the first one, which is ranking and recommendation. This is where for the inference platform, we talked about how much we can use. I'm going to skip some of this, or maybe we'll quickly run through it and we can take offline questions. What this shows is basically when we did analysis of what kind of requirements you have from bandwidth and a latency perspective from the media that you're serving these models from, there is a variability for how much capacity you need and what kind of bandwidth you need and what latency you can live with that allows you to choose between what media you have. Can you use NAND or can you use memory? What kind of trade-off you can do? So that's something that we can again take it offline. I can talk about why there is a performance bandwidth trade-off, performance capacity trade-off we have. Caching, again, I'll let you catch up on the separate email and we can separate file set as we published, but the cache is the large use case in Meta that we use, and that is a significant part of this. CacheLib is a significant, important library that we use, and this has been open sourced already. So this is something that as we go through SDM, CMS as a work, we are making this as available benchmark for any solutions that are getting defined for CMS. And you can really run that as a benchmark and a metrics so that when we look at these solutions, we can text what's the effectiveness of those solutions. So from memory pyramid perspective, essentially what CXL and this CMS is going to offer us is that we had that one blob of HBM to NAND in between the DRAM, and the only way we can scale for the performance requirements was basically to do that trade-off to picking up those solutions. As we see the CMS, what we are going to get is we get now new to kind of a tiers, you can say, the CXL-based memories which could be bandwidth optimized, or then there may be something which may be more capacity optimized. And how to use the tiers between this DRAM to bandwidth memory or tier DRAM to capacity memory, this is where a lot of software enablement is required. This is where Meta has worked on something called as transparent page placement in the kernel base. Our CacheLib also is aware of basically how to take advantage of such different tiers. But that's exactly what allows us to create the most efficient solution by making sure that we got the right capacity and performance to optimize the TCO. Solution perspective, as we start looking into the OCP and start building on the specs, where it is going to be important, what Samir was talking about, that we want to get the solutions which are practical and right now what we can start using it. This might lead us saying that, okay, what is a CXL memory buffer, which will have a bunch of memory modules that can connect to memory DIMMs that you can connect to a CXL ASIC, or it could be a memory module that may come in the standard form factor, whether it is E1.S, E3.S, or anything that comes close to that kind of a solution. So we, as CMS work starts getting done, work starts getting kicked off, this is where I think we'll start focusing on contributions coming from specification perspective. So in general, what we say that CXL brings really three things that to the table, right? You definitely have the capacities to now go beyond optionality to go beyond DDR, which allows you to, because if you are pin bound, you can add more memory with the CXL extension. You get multi-root capability. You can have heterogeneous memory systems. This allows us to do the capacity performance scaling, scale out, because we can do the pool of memory, and we can achieve the TCO efficiency by using the heterogeneous memory systems as well as being the right kind of a match between the capacity and bandwidth. I have too many slides. Okay, this is one of the examples of how inference systems can actually benefit with multiple accelerators and increase the memory with CXL attached to the 2P system. So in general, I think what we are looking for is that we are really looking for industry alignment for this hardware specification, software contribution, benchmark and metrics, and to repeat what Samir Rajadnya was saying, let's make sure that we have practical solutions to start with as we start beginning to evolve to much more complex and much more evolved solutions for the tomorrow's problems. With that, let me ask Renu to cover the virtualization use case.
For 5 minutes?
Yeah, it's okay.
Hello. Okay. I'm Raman. I'm here from Vmware. Where do I use the clicker or do I use? I'd rather use. Let me see if I can. Does that work? Okay. I think many of you know what VMware does, but a way to think about it, I think Samir covered kind of SaaS from Microsoft, SaaS and a composite set of workloads that they run in the cloud, followed by, I think there was more SaaS-ish from Uber, and then Manoj covered more MLAI. I think this is going back to the roots of where VMware is, and you can see most of the workloads are classical, VDI, databases, and a composition of some of these workloads. There, we do see some in the SaaS and in the MLAI as we go forward, but a lot more of the installed base is in the rooted in the classical workload. So a little bit of flavor of where our perspective comes from that. This is standard hierarchy everybody's seen. At the core, I think there are various approaches to tiering. We will see a combination of just 2 tiers, memory and slower memory. We played that with 3D XPoint and supported that. There's emergence of DRAM and NVMe, and probably the absence of 3D XPoint is causing some people to rethink how do we use that, and maybe introduce something in between the two. I think that's Samsung and a few other people are talking about it. Obviously, you want to be able to share memory across, and again, going back to some workloads, maybe it's in VDI or in databases and others, where you want to be able to extend and expand the memory. And a natural cousin to that is the DRAM with the CXL attached device pool, and then maybe NVMe OF. So these are 4 or 5, 6 different ways to attach memory that we will see. We've done some amount of TCO calculations for various types and configurations, and generally we see with tiering preliminary, I mean, we'll get more improvements as the algorithms and as the techniques evolve over time, as the type of media types come to play. And today we used to have DRAM, 3D XPoint, and flash. Now it's DRAM and flash, and others may emerge. But given what we have, there is at least a 20% reduction in the TCO that we get to see. So TCO, tiering, and the types of tiering and why is beyond TCO. One of the key points I didn't highlight in the first slide is I think vMotion is an important consideration in the VMware context, more so than others, because a lot of the workloads are rooted, particularly in the on-prem world, with availability and operational management. So vMotion is an important characteristic in whatever system we design. That goes back into this, and we go into cluster level management and how do we deal with workload management and workload availability in the presence of tiering is an important consideration as we go about it. With that context, what is memory tiering and disaggregation, and why do you want to see? I think I'm repeating myself here, so I'll skip the slide. The way to think about where we are headed towards the future as part of the kernel architecture is there is going to be presence of DDR, lower cost memory of various types, CXL attached. There'll be composition of different memory types. So the host managed tiering pooling is where we are today, and I think it's called Project Capitola that we announced, and particularly starting with aggressively monitoring all the page usage, active and allocated pages, and be able to tier them. But as we get to multiple tiers in the future, this is forward-looking, high-level design is having in the hypervisor itself, I think maybe Manoj highlighted or Samir highlighted, opaque versus transparent. This is more the opaque design point, if you will. This is where we are headed. So a little bit sample set of benchmarks. We've done some work with, I think, Qasim here is going to talk later. He probably is doing bulk of the work, and he can probably answer more of the questions than I can, with using HammerDB as a proxy for many of the database workloads, as well as Redis memtier benchmark. And the key points to highlight, and I think this is what Vikrant said. So we hit a wall today at certain number of VMs. This is a representative, I think it's sorry about the fonts and everything mixed up there, a certain configuration of a system. Around 6 VMs we hit a wall, and by having a tiered memory and expanded memory, we're able to push that wall beyond, I think. sorry for the animation. You get 2x the VM density as we able to expand the memory pool, if you will. This is for the HammerDB, and similar thing you also see on Redis case. So that'll be the canonical use case that we start with, how to provide a graceful expansion and increase based on the ratio of CPUs and memory in a given system. If we have tiering and pooling, be able to leverage either an adjacent node or a pooled memory node to be able to expand the memory footprint. I'll stop here. I don't think I have anything more. Go ahead. So the ask, I mean, in conclusion, our ask is same, is we want to be able to, VMware is not in the hardware business of buying hardware, but we are in the business of referencing, architecting, and being prescriptive for the hardware that we want to see. So we'd be actively involved through this OCP forums and other forums to be able to define what makes sense from the workloads that we see in the field, which is the same common things, is involved in the hardware specifications, the reference designs, and the validation, the qualification, spec out certain latency and bandwidth requirements as we go along, as we learn more, and particularly contribute in the benchmarks. I think the VMmark benchmarks are there, the VDI benchmarks, and a few other benchmarks that will probably also help to contribute to increase the wealth of knowledge and be able to do a better system design. Thank you. Right.
If there is any question. Go ahead.
See if I can ask this coherently. I'm a hardware guy, and I'm trying to envision what these pooled memory systems are going to look like.
Mm-hmm.
You know, when I've seen the memory pyramid many, many times in this, conference, and traditionally, each time you drop down a layer on the memory pyramid, the capacity gets much, much bigger. Performance is much, much worse. CXL memory is kind of a little different, right? Like, I don't see the capacity getting much, much bigger, just because you're still basically populating DIMMs on a motherboard somewhere in a memory expansion device of some kind. So if I think so I'm visualizing a rack, and I'm visualizing a small number of servers that are sharing memory from a pooled, memory server of some kind. But that pooled memory server might have the equivalent of 1 or 2 servers worth of memory in it, something like that. It's not a dramatic, huge amount of memory. And so, what I'm asking is my imagination, my vision of this, is it consistent with what you're thinking? You thinking that, like, memory's being pooled among a small number of servers? I've got a memory pool of maybe 32 DIMMs, maybe 48 DIMMs, something like that, and that's the thing that you're using to fix this TCO problem, because that seems to be the thing that everybody's stressing the most about, is the stranded memory in all the servers.
Yeah, I understand what you're saying. I think for the TCO, you can do it for 16 servers, 8 servers, 32, right? And what's that sweet spot? Because as you're suggesting, the additional cost of bringing this new hardware, cabling, right? Does it compensate with the saving? And this is where we need to make a right call. As you were saying, if we take, let's say, 16 server case, and if you're populating with certain amount of memory, the end goal should be we are reducing the memory across these 16 or 32 servers, right? And this is where we have to have some intelligence. In Microsoft's paper, we talk about this VM management, and at the end of the day, we don't want to affect the application's performance, right? So how do we take certain VMs which are not latency sensitive? Maybe they can talk to this pool memory. Some of those were extremely latency sensitive, let them be just on the local DRAM, right? So I think the end goal is to reduce memory with this pool, and that's where the TCO savings will come. If you're populating the same amount of memory, there is no TCO savings.
Sorry.
Go ahead, Sam, good.
So memory pooling is great, and as you just suggested, there is cost of developing memory pooling system. But now with CXL 3.0, memory sharing becomes possible also. So again, this community can think building the same system, presented as memory pool system or memory shared system, and add more value so that so you can extract more value out of the same hardware complexity.
Can I also add CMX point also as a different use cases? Some platforms actually are needing more memory than that can be supported today physically on a given system based on the channels that we can put and the density I can put. So for them, you will see that actually there is a need for memory required, which will reduce some other kind of stranding, because I may need to put more CPUs if I need to get more memory. Having CXL option basically goes beyond that. And then to connect it back to what CMX talked about for how do we pool it and how do we make sure that we are expanding it, not add infrastructure in each servers. I think that can create future opportunities as we start looking to CXL 3.0, et cetera.
Sure. One of the things
One
I'm curious
point
to-
that I maybe to add to what Manoj was saying. In our case, the TCO, thank you. In our case, the TCO equation is like we want the pool memory to be, instead of putting it on the host, we want to say have the pool memory have 50% less memory across instead of putting it on the host. Because what we find is the memory usage is very uneven during the day or during the night, depending on what part of the world Uber is being used in. So that's why we want to make sure the memory is available, but it's more of an empirical analysis that we need to do to figure out what that sweet spot is. So instead of having memory all locked into host which is not being used, going back to the sharing, but how we do it is a different question. But the end goal is to have less memory than what you would have in the host that you would deploy today.
Sure. One of the things that I'll be curious to see how it works out, because in my world, I deal with a similar problem, which is oversubscription of other resources, namely power. And in the data center, we deal with power oversubscription all the time. And ultimately, somebody has to, in the data center, somebody has to sign, or it has to make a decision and say, this is how much we're going to oversubscribe. And the same thing's going to have to happen with pooled memory, right? Because that's the whole point, is improve TCO by oversubscribing memory. And it's a scary thing. It's scary with power, and it's going to be scary with memory, because if you make the wrong decision, the repercussions are very severe.
Yeah, I agree.
If you behave conservatively, you're not going to get any benefit.
Yeah.
And so somehow you have to change human behavior in order for this technology to give the result that you're looking for.
Right.
Yeah, so I think in our case, we have control on what goes on the pool memory versus the host memory. So I guess non-mission critical services of jobs could be allocated there.
Just to add, I think there has to be this feedback path, QoS, right? You have to monitor. Sometimes these predictions can be wrong. So we have to monitor and you have to take corrective action. So
Yeah, there are many emergent use cases over the last couple of decades, and more so coming lately. But there is operational benefits, there is TCO gains, there is performance needs as constraints. But one thing that really to bound this problem is, the good news is sometime back we went from a single address space shared memory to a 2 NUMA hop as a programming model and optimize everything. So what CXL did, the law of unintended consequence, was being able to go from a single address space shared memory to a purely scale out to have small radix clusters and being able to get to a performance model that is acceptable for most use cases. So that's the constraining factor that has to be overlaid into all the other benefits may come. We may not see beyond the 2 NUMA hops as a design point, I think, and then look at the operational gains, the cost gains, in some cases the workload performance gains, and other things has to be overlaid. So we are in the journey. We don't know the final answer. I think we're just starting on the journey to, within that constraint, to fit what all things can fit.
I think we are on the top of our, but can we maybe take one question and then?
Yeah, I was wondering if, corresponding to your kind of memory hierarchy, that there's a corresponding thought on the system shapes that sort of enable that. So we think of it as, host-attached, memory, at least in the current version of CXL, for example. It's all pretty much inside the server, right? And think about this pooling and how to get this efficiencies across, let's say, 8 or 16 servers. that requires some kind of system shape, and there's obviously resiliency and other things that go with that. Is there any thoughts now as to like how a pooled system will look?
Do you want me to take a?
Go for it.
Let me just quickly maybe summarize and say that this is exactly what the work will start happening in this group, that there are going to be at least across 4 work streams that we are looked at. That what are the use cases, what are the kind of shape, if you will, for the local native memory expansion, then what will be for the pooled storage, then perhaps even further going out with the switches and the systems, and then near memory compute. I think the contributions will come from different aspects. There will be hardware contribution, software contribution, but all of them will be driven by these requirements that many use cases are going to drive. And the shapes will be different, but what we want to make sure that we can have common configurations that can be leveraged across the industry. Those are going to be electrical, mechanical, and kind of a form factors that you can get the right hardware design. You can get right software components which can scale to the different level of a shape of the system, if you will, if I got your question correctly. And that's something that is what the group will work together, that allows us to build the different systems for different requirements, but make sure that actually we are addressing it in a consistent fashion so that we don't have to go and build very unique solution ourselves. All of us basically who are driving the requirements.
Yeah.
Does that answer your question?
Yeah, sort of. I think the point was that if you actually go to pool outside the server or share across servers, that sort of implies a disaggregated system, in addition to kind of a disaggregated logical topology. And that means that you have an element that can connect to many different other types of server hardware. And if that's one of the goals of the group in terms of defining that, I think there's a lot of interest in external inputs that could drive.
Absolutely, absolutely. And by the way, this is, now we are just starting, so please do join this discussion so that we can really have that discussion and drive it in the direction which makes sense and we are in the right direction, not missing out something.
Thank you.
All right, thanks Samir, I think thanks Renu and Vikrant. We can maybe go to the next session now. I know we are not getting a break right now unless everybody really thinks we need to take a break. Otherwise, we'll take this one session and then take a break. Reddy and Rekha, do you want to run to the next session?